In this video, we present our paper verifying the unseen interactive proofs for label-invariant properties. In 1943, a group of researchers were investigating butterflies on Malayan islands. Never intending to catch all the butterflies, they were interested in estimating the number of different species they catch while roaming the island. Essentially, they asked the following question. Say I can sample a distribution. How many samples would I require to know the distribution's support size? This question, and perhaps also an awe of butterflies, has inspired statisticians and computer scientists. Take, for example, a natural follow-up. Given samples from distribution D and the bound on D's support size, how many samples are required to estimate D's Shannon entropy? Well, it turns out that quite a lot. In order to approximate the entropy, almost linearly many samples with respect to the maximal support size are needed. To put it in context, using linearly many samples, it is possible to produce an explicit description of a distribution arbitrarily close to the distribution sampled. And so, this lower bound essentially says that estimating entropy is not much easier than approximating the entire distribution. Not only this, it also extends to other statistical measures, such as approximating the distance from the uniform distribution, estimating the support size, and more. We therefore learn that approximating interesting measurements of a distribution might be quite costly, and not significantly better than approximating the entire distribution. Which leads us to the motivating question of our work. Is verification easier? Where the definition of verification is inspired by the seminal work of Goldwasser, Micali, and Rakoff, and is as follows. Say that a verifier V that has sample access to distribution D, that is, it has black box that generates samples from D, is told that the entropy of a distribution is roughly K by a powerful yet unreliable prover. Is there an exchange of messages between them, at the end of which the following conditions apply? If the entropy is indeed K, and the prover follows protocol, then the verifier accepts with high probability. But if the entropy is far from K, then no matter what a cheating prover might do, V will reject with high probability. Of course, we are interested in the case that this is efficient, that is, V's runtimes and sample complexities, as well as the communication complexity, are all sublinear, while the number of rounds is small. Broadening our scope beyond entropy, how about verifying other claims and properties of distributions? This line of research on the intersection of interactive protocols and distribution testing was initiated in 2017 by Chiesa and Gur, and our result expands on it. For the case of verifying entropy, we show that there exists an interactive protocol for verifying that the entropy of a sampleable distribution D is K. In this protocol, the verifier and prover exchange only two messages. The verifier draws roughly square root of n samples and runs in time also square root n. The communication complexity, that is the number of bits transmitted in the interaction, is also of the same magnitude. To put it in context, think of the following two protocols for the verification problem, representing two possible extremes. Number one is ignoring the prover altogether and conducting the approximation of the entropy alone. For this task, as said before, almost linearly many samples are needed. On the other hand, if we allow very high communication complexity, the prover can send the entire description of D, stating the probability of each element, and the verifier can just check whether the statement is correct. A known result in the field of distribution testing shows that this can be achieved with roughly square root of n samples. Our result, in contrast, has both the sample and communication complexity low. We note that we cannot expect to get smaller sample complexity than square root n, no matter what the communication complexity or number of rounds is. Another important thing to note is that the running time of the honest prover is superpolynomial in n. Our result extends to more than just entropy approximation, and in order to phrase the theorem in a more general setting, we use the language of distribution testing. And so we take a small detour to define some relevant terms. Distribution testing is the field of deducing properties of distributions using a small number of samples. We present here two fundamental definitions in the field. The first is the idea of property. A property is a family of sets of distributions, each set is indexed by a natural number that signifies the size of the domain of all the distributions in the set. We say that the distribution over n elements has property pi if it's in the nth set in the family. For example, consider the property of being uniform over the entire domain. This property is the family of singletons of the uniform distribution over n element for each n. Similarly, the property of having k entropy is the collection of distributions with entropy k, again indexed by the domain size. Lastly, we call a property label-invariant if permuting the domain does not change the property at all. For example, the two properties above are label-invariant, since renaming the domain elements doesn't change the entropy, nor does it make a distribution uniform over n elements not uniform. While the property, for example, of assigning half the mass to the first element of the domain is not label-invariant. Going back to our result, in the language of distribution testing, we show that there exists an interactive protocol for verifying the membership in every label-invariant property, and I'll explain the asterisk at the end, such that this protocol consists of only two messages. It has communication complexity, verifier sample complexity, and verifier runtime, all of magnitude square root n, up to log factors, and again, the prover runs in time superpolynomial. For sake of simplicity, instead of sketching the proof, we present an example of a specific problem for which our protocol provides a significant improvement over the non-interactive solution. We start by presenting the problem. Fix some n and epsilon and consider these two families of distributions. DC consists of distributions that have 90% of their mass on elements with probability 1 over n, represented here in blue, and the rest 10% on elements with probability 1 plus 10 epsilon over n, represented in red. DF consists of distributions with their mass split equally between elements with probability 1 minus 8 epsilon over n, represented in green, and again, elements with probability 1 plus 10 epsilon over n, represented in red. Assuming that we have sample access to distribution D that is promised to come from either DC or DF, we want to distinguish the case that D is in DC, which we consider the yes case, or D is in DF, which we consider the no case. We can think of this problem as distinguishing between distributions close to the uniform distribution of the entire domain N and distributions that are far from it, where the promise is that the sampleable distribution D is from one of these two families. In order to perform this task without communication, at least n to the 2/3 samples are needed. This is due to the fact that in any smaller sample, we expect to see roughly the same number of elements appearing once and twice, no matter if we sample from distribution DC or from DF. While we don't expect to see any elements appearing 3 times or more. And so, the small sample cannot help us distinguish between them. Without going into details, this is related to the distribution's L2 norm, which is the same for any distribution in both families. However, when we sample n to the 2/3, there starts to be a significant difference between the collision patterns in each family, and the number of elements appearing 3 times in a distribution from DC will be significantly smaller than the number of such elements in distributions from DF. We show that through interaction with the prover, the verifier can distinguish between the cases with high probability using only square root of n samples. Later, we explain how the ideas we are about to present here are extended to achieve the general result. We now present the protocol. First, the verifier starts by sampling S samples and sending them to the prover. The prover then replies with the claim of the probability of each element in the sample, in this case, whether each element is blue, red, or green. The verifier checks to see whether the color histogram of the sample matches a possible sample from a distribution in DC, that is, whether it's 90% blue and the rest red. After this test, it proceeds to perform a second test. The verifier samples S new fresh samples and checks to see how they collide with the previous sample that the prover already tagged. The important insight here is that we expect a certain number of collisions between the samples. For example, we expect any first sample in Y to collide with a given blue tagged element with probability 1 over n, as this is the probability of real blue element. As there are roughly 0.9 times S blue-tagged elements and S fresh samples in Y, the number of blue collisions we expect between the samples is as shown. Since we picked S to be in the order of square root n, we are assured that such collisions will occur in expectation. If the prover is truthful, these two tests pass. The first test passes as the empirical distribution of colors is close to the true distribution, and the second one passes from concentration of measure arguments, and due to the choice of S. If the prover is lying, these two tests pose significant constraints over its answers. However, they do not suffice, and a cheating prover can still pass them. Assuming D is in DF, we show a cheating strategy for our prover. V sends a sample from D which has green and red elements. Then the prover smushes it, meaning that it labels all green elements as blue and 80% of the red elements as blue, while the rest are red. This false labeling has the property of passing both tests. 90% of the samples are tagged blue, while the rest are red, and thus the first test passes. But also the collision test passes. This is because the elements tagged red are indeed red, and so the expected number of collisions they will have with the second sample is close to the expected value derived from the histogram. The case of the blue tagged elements is a bit more involved, as all samples tagged blue are either in fact red or green. Red elements are more probable than blue ones, and so are more likely to collide with the sample Y, while green elements are less probable than the blue elements, and so are less likely to collide with a new sample. This mix of elements that are more likely and less likely to collide balances out, and the expected number of collisions between the fresh sample Y and the blue tagged samples is exactly the same as in the case that all the elements tagged blue were actually blue. However, we will show that this smushing, so-called, has an undesired effect for the prover. We focus our attention on the elements tagged blue. As 90% of the sample is tagged blue, the prover essentially claims that 90% of the mass of the distribution is on blue elements, where in fact, of this 90%, 5/9 are green and 4/9 are red. Therefore, if we think of distribution Q representing 90% of the mass of the distribution, it is in fact composed of 5 parts green and 4 parts red elements normalize. What the prover claims it's a uniform distribution with each element of blue mass. These two distributions have a noticeable entropy gap. In other words, considering the part of the domain represented by the blue sample, the smushed distribution has less entropy than the real distribution. This result is not unique to the strategy we presented. In fact, we show that every smushing, that is, a prover strategy that passes the collision test, must result in a similar outcome. This stems from this lemma, which states that the distribution that is far from the uniform distribution over k elements, yet has the same collision probability as the uniform distribution over k elements, must have higher entropy than log k. This is exactly what happened in the smushing attack. The prover claimed a certain distribution was uniform, that is, all blue in our case, when in fact it was far from it. It was red and green. At the same time, the collision probability of this alleged distribution is so-called correct, that is, similar to the collision probability of the uniform distribution. This is the guarantee provided by the collision test. And so, we conclude that given a labeling of the sample, a verifier has obtained an approximation of the color histogram of the entire distribution, from which it can compute an approximation to the entropy of the distribution. If the prover is truthful, with high probability, this claim will be close to the true entropy of the distribution. Otherwise, we have shown that either the first tests fail, or, if they passed, then the prover has resorted to smushing, yielding a coloring of the sample that induces an entropy claim that is significantly smaller than the true entropy of the distribution. We are now ready to wrap up the protocol. After performing the collision test for both blue and red samples, V computes an estimation of the entropy of D achieved from the sample histogram. We are now left to identify the case that this entropy claim is close to the real entropy, or significantly smaller than the real entropy. This is achieved by an entropy upper-bound protocol taken from the statistical zero-knowledge literature. This provides us with exactly what we need, a protocol with small sample complexity and small communication complexity, where the verifier accepts if the entropy is bounded from above by some value and rejects otherwise. We are done. We have shown how to distinguish between these two families of distributions while using only square root and samples instead of the n to the 2/3 required for testing. But how does this extend to the general case? In the general protocol, we wish to determine whether a distribution is close to or far from some given label-invariant distribution property. This is achieved by first obtaining an approximation of the probability histogram of the distribution, that is, how many elements are of each probability. Since we deal with label-invariant properties, this information suffices for concluding whether a distribution is close or far from a property. And so, we show how we obtain a verified histogram of a distribution. As before, the verifier draws S samples and asks the prover, once again, to color them according to probabilities. Only this time, the prover is not limited to a small set of colors, but it has a much larger palette at its disposal. For each element sampled, the prover returns an integer indicating to which probability bucket it belongs to, where the jth probability bucket contains all the elements in the domain with probability roughly e to the j epsilon over n for some accuracy parameter epsilon. This is a discretization of the possible probability range. We note that we disregard elements with very small probabilities, and so this color palette is not too big. As before, at this stage, the verifier has obtained a claim about the histogram of the sample, and if the prover is truthful, with high probability, this histogram is very close to the true probability histogram of distribution D. Now the verifier is left with the task of verifying this claim. It continues in the same way as before. The verifier samples a fresh sample Y and performs the collision test for each bucket. This collision test assures us, as earlier, that if it passed, then either the prover was truthful, or that some smooshing has occurred. And again, the verifier computes an estimation of the entropy of the distribution and performs an entropy upper-bound protocol. Now, the verifier has obtained a probability histogram of the sample. Using this histogram, it can decide the membership of D in many label-invariant properties. This is also where the asterisk in the theorem statement is explained. The verifier's runtime is of magnitude square root n up to log factors as long as the property in question is easily deduced from the histogram. Otherwise, the verifier runtime of the protocol might exceed this figure. On a technical level, this protocol contains 4 messages. However, we use some technical tricks to collapse the number of rounds and have only 2 messages. Lastly, we mention here a few details swept under the rug, as the full protocol has plenty more fine details. First, it makes a distinction between heavy and light elements, where the protocol shown here is the one performed over the light elements only, while the probability of the heavier elements is explicitly approximated. Moreover, the process of deducing the property from the histogram is not always immediate, and for some properties it might also involve interaction with the prover. This interaction can be pushed into the protocol. Lastly, we remark that the high runtime of the honest prover is a consequence of the entropy upper-bound protocol. The immediate open question we face are whether the prover can be made more efficient, which we think it can be, and also we want to improve the dependency on epsilon as well as cutting log factors. Finally, we point in the direction for future research, be it by achieving similar results for other properties, or designing protocols with certain characteristics, like public coin. Moreover, we hope for applications of similar ideas in other fields, like verification of machine learning algorithms, as in Goldwasser, Rothblum, Schaffer, and Yodayev. Thank you.